This is a story of a man who was chased by a gazelle? Eventually the man reached a wooden beam that was overhanging a cliff. He jumped onto the beam and made his way to the end. Then he turned around to face the angry gazelle. To save himself, he had only one option left. He lit his torch. And the gazelle was scared and backed away. This is one possible outcome. But there is another possible outcome. He may reach the end of the beam, but then the beam starts to rotate, and the man goes over the edge and tumbles to his death on the rocks below. Will the man tumble to his death, or will he not? That is our first question. To answer this question, we should consider all the forces which act on the man and the beam. There's the man standing on the edge of the beam, at the left side. Let's consider each of them separately. So let's represent the man as a dot. And let's draw all the forces acting on the man. First, there's the force of gravity acting downwards. That's Fgm, where m is for man. And then the beam exerts an upward normal force on the man. Fn B on m, for beam on man. The man is in translational equilibrium. So by Newton's second law, the net force on the man is going to equal 0. So in the y direction, and we take up to be positive and down to be negative, the sum of all the forces in the y direction is Fn B on m minus Fgm, and that's going to equal 0, because he is in translational equilibrium. And we can solve this for Fn B on m equals Fgm. And if the man has a mass of m1, then that equals m1g. The man exerts a normal force on the beam, right where he is standing, at the left edge of the beam. And that's called Fn m on b, for man on beam. By Newton's third law, these two normal forces have the same magnitude, but opposite directions. So we can write this, Fn m on b equals Fn b on m. So therefore, the normal force of the man on the beam is equal to m1g. Another force acting on the beam is the force of gravity, Fgb. It acts at the center of the beam, which is the center of mass of the beam, assuming the beam has a uniform density. The other force which acts on the beam is the normal force which the ground exerts on the beam. And I've just put it acting right here, but we don't know the exact position at this time, but we will find it out later. One thing we do know is that the normal force has to be to the left of the edge of the cliff, because it is the force of the ground on the beam. And there has to be ground there to exert the force. So here we have ground, but here, to the left side of the edge of the cliff, there is no ground. So the normal force has to be exerted to the right of the edge of the cliff. And I'll call that normal force Fn G on B, for ground on beam. These are the three forces acting on the beam. If these three forces produce a torque which is counterclockwise, then the beam will rotate counterclockwise and the man will fall to his death. If these three forces produce a torque which is 0, neither clockwise nor counterclockwise, then the man will be safe and the beam won't rotate. It will be in rotational equilibrium. Let's look at each of these forces. Fn m on v, the m1g. It causes a torque which is in the counterclockwise rotation, as shown here. It produces a counterclockwise torque about the edge of the cliff. And it cannot cause a clockwise torque. If it was exerted to the right side of the edge of the cliff, then it could cause a clockwise torque. But it is exerted to the left of the edge of the cliff, and it causes a counterclockwise torque. Now let's look at the force of gravity on the beam. As shown here, it exerts a torque in the clockwise direction, about the edge of the cliff. And it cannot cause a counterclockwise torque. If it was exerted at the left side, to the left of the edge of the cliff, then it could cause a counterclockwise torque. But since it is to the right of the edge of the cliff, it only causes a clockwise torque. And now we have the force caused by the torque caused by the normal force of the ground on the beam. As shown here, it causes a counterclockwise torque. It is interesting to note at this point that once the beam starts to rotate in the counterclockwise direction, there can no longer be a normal force applied by the ground on the beam at this point, because there is no ground there to exert the force, and so no torque would be produced. So it causes a counterclockwise torque about the edge of the cliff, but what it really is doing, it is preventing any clockwise rotation from occurring. But it cannot cause a clockwise torque. So here are the three forces which act on the beam. If the man is going to go over the cliff, the beam rotates in the counterclockwise rotation, the net torque is counterclockwise. And if we say the counterclockwise direction is positive, then the sum of all the torques is going to be greater than 0. If the man is not going to go over the edge of the cliff, if he's going to be safe, then the net torque is going to be 0. And we can write net torque equals 0. So when we look at this problem, we don't need to consider the normal force which the ground exerts on the beam. We only need to consider m1g and m2g. If the torques caused by m1g and m2g are counterclockwise, greater than 0, then the man is going to go over the edge of the cliff, because the normal force of G on B only causes a counterclockwise torque. It will not prevent the man from going over the edge of the cliff if the other two forces produce a counterclockwise torque. So let's just consider the torque caused by these two forces, m1g and m2g, to determine whether or not the man will go over the edge of the cliff. Let's get some numbers here. Let's say the mass of the man is m1 equals 60 kilograms. The mass of the beam is m2, which is 150 kilograms. The beam has a length of 7 meters, as shown here. L equals 7 meters. The force of gravity is applied at the center of the beam, at a distance of L over 2 from the left edge of the beam. For this experiment, the beam overhanged the edge of the cliff by 2.0 meters. As shown here, R1 is 2.0 meters. And if that's the case, then R2, the distance from the edge of the beam to where the force of gravity is applied, is 1.5 meters. R1 plus R2 equals L over 2. So 2 plus 1.5 is 3.5, which is 7 over 2. Now let's look at the torques about the edge of the cliff caused by M1G and M2G. Torque 1 E plus torque 2E, where E refers to torques about the edge of the cliff, it equals R1 M1G. So force M1G provides a counterclockwise torque, which is positive. Then we subtract R2 M2G. The torque caused by the force of gravity M2G is clockwise, so it is negative. The sum of these two, if we put in the numbers, we get 2 times 60 times 9.8 minus 1.5 times 150 times 9.8, and that is negative 1,029 Newton meters. That is a negative number. That is a clockwise torque. So the man is not going to go over the edge of the cliff. The man will be safe. The torque caused by the normal force of the ground on the beam will provide the necessary clockwise torque to allow the net torque of the three forces to be 0. Now let's look at the magnitude of the normal force of the ground on the beam. Here are the three forces on the beam. The beam is in translational equilibrium. That means that the sum of all the forces in the y direction is going to equal 0. Let's take the upward direction to be positive and the downward direction to be negative. So we can write this summation as Fng on B minus M1G minus M2G equals 0. Solve this for Fng on B. We get this, M1G plus M2G, or M1 plus M2 times G. Let's put in our numbers. We get this, 60 plus 150 times 9.8, which is 2,058 newtons. So that is the magnitude of the normal force of the ground on the beam. Now we want to find out, where does that normal force act? We know it needs to be to the left of the edge of the cliff. Let's find the exact value. The beam is in rotational equilibrium, which means the torques about any point is going to equal 0. So we can take the torques about any point on the beam. It's convenient to take torques about one of the locations where we know what the force is. So right here, where the forces act. So let's take the torques about the left end of the beam. The sum of those torques has to equal 0 if it is in rotational equilibrium. Let's say that the normal force of the ground on the beam is applied at a distance x from the left edge of the beam, as shown here. And the force of gravity is applied at a distance of L over 2 from the left edge of the beam. That's at the center of the beam. Let's write the net torque equation. So x times the normal force times g. This is a positive value because it is a counterclockwise torque, minus L over 2 m2g. That is negative because it is a clockwise torque. And the sum of those two is 0. So do some manipulations. Let's substitute in Fng on B. It is m1 plus m2g. So put that over here and solve for x. We get this, m2 over m1 plus m2 times L over 2. It is interesting to note that this factor, m2 over m1 plus m2, is less than 1. That means that the normal force is applied over here, between the edge of the cliff and where the force of gravity acts. That makes sense, because the normal force is larger than the force of gravity, so it must be applied at a shorter distance from the left edge of the beam. Putting in our numbers, we get this, 2.5 meters. So here's what it looks like. We have the normal force applied at 2.5 meters right here. Force of gravity is at 3.5 meters right here. The net torque from these two forces is equal to 0, and the beam is in rotational equilibrium. When we did this calculation, we didn't make use of the fact that the beam overhanged the edge of the cliff by 2.0 meters. That didn't come into our calculation. Well, here it makes sense that the 2.5 meters is where the ground is. So that's certainly a normal force can be produced at a distance of 2.5 meters. But what if the beam overhanged the edge of the cliff by, say, 3.0 meters? Something like this. Here's 3.0 meters from the left end of the beam to the edge of the cliff. Again, our force of gravity is applied at 3.5 meters from the left edge of the beam. But look at our normal force. It is still applied at 2.5 meters, right here. But what do you notice about this point? At this point, for this situation, there is no ground there. There's nothing to exert the required normal force, which means the man will fall to his death. This normal force cannot be applied. Therefore, the beam will rotate. Here's a summary of what we've learned in this presentation. First of all, we did not have to consider the normal force of the ground on the beam to determine whether or not the man falls to his death. The normal force of the man on the beam causes a counterclockwise torque, and the force of gravity on the beam causes a clockwise torque. We just need to consider the sum of these two torques to determine whether or not the man will fall to his death. If the sum of these two torques is counterclockwise, then, unfortunately, the man will fall to his death. If the sum of these two torques is clockwise, or zero, then the man will not fall to his death. We were also able to find the magnitude of the normal force which the ground exerts on the beam. We did that by looking at the condition for translational equilibrium. We could find the position where the normal force was applied by looking at the condition for rotational equilibrium. What's this? Is that a cannon? The man is pushing a cannon. He's still alive. Our calculations were correct. But what's he doing with a cannon? Oh no. Oh, he does this stupid experiment where he shoots a gazelle out of a cannon to study projectile motion. I told him not to do it anymore. This is animal cruelty, and it's not happening on my channel. Oh no, he's chasing the gazelle. Okay, I've got to get down there right away and put a stop to this. Let's wrap this up quickly. Thanks for watching this presentation. Please be sure to like and subscribe. Leave a comment in the space below. I'll see you next time. Bye.